So, here are the rules. Every Tuesday when you walk into class, you'll see a new problem set here. Okay. You will also then turn in your problem set by stapling that sheet, the problem set sheet that you got, to a separate sheet that has your work on it. Okay, so you don't do the work on that problem set sheet. You do the work on a separate sheet, and you staple the two together when you turn it in. Okay, this will be a ritual that will go on now for the rest of the year. Okay, every Tuesday is a problem set day. Okay, here's why we do them. I have found that throughout my time teaching math and trying to get students to do good quality work, that it's really hard, because if I say, I'm going to check your homework, I could check your homework all the time, but then we'd have to be checking every single problem. And sometimes it's just better to just allow you to experiment while you're doing your homework. Okay? So if I say, all right, let's wait until we have a quiz, then I'm waiting till the quiz to actually tell you what you're doing right or wrong. And then that's actually too late. Or worse yet, I wait till a test to tell you what you're doing right and wrong. Okay? So the way that I've decided to do it is, when you do your homework, you can do it however you want to, but I would encourage you to use good notation. But the problem sets is all quality work. It's the best work that you can do where you justify everything. This way, you are demonstrating for me the best you can do. And you don't have to do that in your homework, because that's where you are just kind of just figuring stuff out. But this is where it's the best thing. The problem sets, also, the problems that appear on the problem sets can come from anywhere. So anything that we've ever done is fair game on the problem sets. Okay? This is another way that I try to spiral your work so that you don't depend on just studying something and then forgetting it. Studying something and then forgetting it. That's not how this works here. You are expected to remember everything that we've ever done, or if you don't remember it, to figure it out. Okay? So because on the day of the test, of the exam, that is, for the AP exam, I don't expect you to just cram the night before to study for this. No. We're going to do all the work all along the way so that when it comes to the exam, you are ready to go. Question?
Is justifying just as far as like showing each step that you do?
Yes. And sometimes there's cases based upon the question. For example, look at that last one. It says, determine whether or not the statement is true or false. Okay? So if it's false, then you have to explain why or give some sort of counterexample that demonstrates it. Okay? So that's where you're explaining it. And you're explaining it mathematically correct. And I am very, very picky when it comes to grading these, just so you know. Okay? Any questions? All right, we'll get more questions cleared up as time goes on that. So think of the things that we got going on. You have your regular homework that you got to do. You got the chapter summary that you have to be working on for the chapter that we're in. And then you'll have the continual problem sets. Those are the three main prongs of what we do here outside of class. Okay, this is where the work starts to begin. So you got to make sure that you're setting time aside for it. All right, well, here's what we're going to do. Today and tomorrow, I'm going to be explaining problems from that current assignment. Just to let you know, here's the deal. Page 67 is due Thursday, and page 68 is due Friday. On your homework sheet, it's listed as part 1 and part 2. Okay? So we're going to have everything done from these two sections you do all of the homework and have it done by Friday. I have one good correction for you. Pull out your assignment guide. And on part 1, you get to cross off a few problems. At the end of that, it says problem numbers 51 through 59 odd. Okay, 51 through 59 odd. I'm making a correction on that, and you can cross off these, and you only have to do the 51. Good. Those were hard ones. It's a different technique to do that. Okay. All right, let's move on. We're going to do some problems, and then we're going to develop some properties and rules along the way. So you can. I think you might want to copy down the problems that are on the backboard. We got one problem we're doing it 4 different ways. And make sure you get me your permission slip, so as you may appear on the video, you got that. Okay. And by the way, don't be surprised if we have random pop quizzes that I tell you nothing about, of things that we've covered. Okay? So it's my way of also just seeing if you're paying attention and possibly doing your homework. So here we go. I'm proposing 2 limits here. Let's suppose we have a limit as x approaches some value of c, it can be any number on the x-axis, of a function f of x, and the answer is 3/2, or 1.5. And then at the same time, I've got another function, g of x, where as x approaches c, the limit is 1/2. And then with knowing those 2 things, let's answer these questions over here. And we're going to develop some properties along the way. Yes, this whole week is 1.3. And just to give you a clue, perspective, we're going to wrap up limits next week. Okay, limits are going to be all done, and we're going to start on derivatives right away. Okay, so let's take a look at this first one. It says, what is the limit as x approaches c of 4 times f of x? Limit as x approaches c of 4 times f of x. I'll take a suggestion from you, and then we'll ask for a reason why it is, and then we'll see if we can maybe draw a conclusion or make a rule about that. Any guesses? 6? Anybody else say 6? Where'd you get the 6 from? So you said 4 times 3/2, and that's the answer of 6. Okay? That is actually correct. Okay? But why can you do that? How come you can just multiply that? Bailey? Okay. Do we know if the function is continuous at this point? We just know that the limit is this 3/2. Okay. So I don't think that quite answers it. It's in there somewhere, though. Yeah. Okay, good. Do you guys really know what it means to have 4 times a function? Stop and think about it. What this really means, if I say, what does 4 times f of x mean? Well, if you picture, you've got some function. Maybe it looks like this. Okay, and this is my f of x. Okay, if I multiply that function by 4, then every single y value is being multiplied by 4. Meaning, whatever this one was, let's pretend this was this is 1 high. Okay, just 1. The function 4x is 4 times 1, and it's up to 4. 2, 3, 4. That's what it does. So the function actually goes up here. This value is 0. 4 times 0 is 0. Let's just pretend this one is at negative 1. 4 times negative 1 is negative 4, so I'll put it down here. So if I graph 4x, it's going to look like this. And so on. It stretches it. It makes everything 4 times the magnitude that it was. Okay? So if I had a limit and x was approaching c, and c was, I don't know, I'll throw it right here. Okay, whatever this value was. This is what the limit was. Okay, this is that 3 halves. Well, that's not where 3 halves would be. But whatever this value is, the answer to the limit is 4 times it. Okay? Because when you multiply a function by a number, you're stretching it either a positive or negative direction by that magnitude. Okay? Now, we can summarize this with a property. And so we're going to make a little list of properties here for limits. The limit as x approaches, I'll say c, of f of k times f of x is equal to k, look at how I'm writing this, times the limit as x approaches c of f of x. Look carefully at what I'm doing here. The limit as x approaches c of some number, this is called a scalar multiple, physics we call it scalars, of some number times f of x, you can actually just take the number and then multiply it by the limit. If you want to put it into words, I'd read it like this. The limit of a constant times a function is equal to the constant times the limit of the function. Okay? So that's the rule there. If you want to get really simple on this, which a good problem solving thing is, if you have something that's complicated, make a smaller version of it. And see if you can see if it makes sense. So watch this. What if I did the limit as x approaches 2 of 3x? Now you guys would say, what's the answer? 6, because you can plug it in because that's a line, right? But watch, if I apply this rule, I can really say, hey, you know that 3? You can actually pull that 3 out. And it's 3 times the limit as x approaches 2 of x. And that's where we get the answer of 6. You can pull the constant out when there is a limit being multiplied by a function. You see that? And this is the super simple example. I pulled out the 3, boom, boom, and I really have 3 times 2, which is the 6. Okay? First property. All right, second one. Limit as x approaches c of f of x plus g of x. What's the answer here? 2. 2 is correct. Okay? And it comes from, well, the limit of the f of x, that's 3 over 2, plus the g of x, which is 1 over 2, and so the answer is 2. Okay, so let's make a property for this. The limit as x approaches c of f of x plus g of x. What I'm really going to say here is the limit of a sum of two functions is actually equal to the sum of the limits of the two functions. Limit of the sum is equal to the sum of the limits. So this is going to be written as the limit as x approaches c of f of x plus the limit as x approaches c of g of x. In other words, when you're taking the limit of the sum of two functions, you can sum the limits. Okay? We actually do this all the time. Separate example there. Limit as x approaches 3 of x squared minus 5. Well, I'll put a plus 5. We learned yesterday, graphically or visually, oh, that's a parabola, shifted up 5. If I can, that way I can plug it in. But if I want to do it analytically, I can say, well, you know what I can do? I could separate this. The limit as x approaches 3 of the x squared plus the limit as x approaches 3 of the 5. This answer gives you 9. This answer gives you 5. And the answer is 14. So it's a justification as to why you can do it. Limit of a sum is equal to the sum of the limits. You can also modify this. If I put a plus or minus symbol in here, okay, meaning I can subtract as well, then the corresponding rule fits over here. The difference of the limit of a difference of two functions is equal to the difference of the limits of the two functions. Okay, third one. Answer? 3/4. Okay, because we're really taking 3 halves multiplied by 1/2, and that answer is 3/4. Go ahead and write the rule like I've written the other rules. Go write the rule like I wrote the other rules. And then be prepared to say it the right way. Okay, who can say this the right way? Following what I did in the other ones. Try it, Bailey.
Well, when they f of x times g of x is x approaches c equals the limit of f of x as it approaches c times the limit of g of x as it approaches c.
Okay, very good. That's how you can read this very technical manner. Very good. Can anybody generalize it now? Where this was the limit of a sum is equal to the sum of the limits. This is the limit of a product is equal to the product of the limits. Okay? The limit of a product is equal to the product of the limits. Okay? All right, last one. We get the picture here. 3 halves divided by 1/2, which is what? Three. Remember, you can do it lots of different ways. Popular way would be maybe to multiply both the top and bottom by 2. Those, therefore, the 2's cancel, and you get an answer of 3. Or you could use your old division way of doing fractions. Okay, write the rule for the last one. Okay, limit of a quotient equals the quotient of the limits. Right? There we go. Okay, let's move on. There's a couple of rules that these ones you need to memorize. Okay, this is a couple of our foundation here. So very few times I ask you to memorize something. So let me show you the first limit. It's actually used in engineering a lot. The limit as x approaches 0 of the sine of x divided by x. All right, if you were going to try to figure this out, you'd say, okay, can you visualize this graph? It's a little bit tricky to visualize. Okay, you got to take the sine value and then divide it by that same x value. Okay, so is it continuous? Well, can we plug in the 0? No. We get the denominator is 0, but worse yet, the sine of 0 is also 0. So we get 0 divided by 0, which I gave a name to that, indeterminate form. Okay, so all right. So the next way, which you're not going to be allowed to do this on any sort of test or on the AP exam, but I want you to figure this out. Pull out your calculator. Get me the answer to this. Now, I like to do a zoom 6, so everybody's got it in the same spot here. And I don't know if you know this feature. I'm having a hard time seeing exactly what's going on here, so I'm going to do a zoom box. Okay, zoom boxes are cool. Okay, so hit zoom, and then it's the first one, and then you get to make a box around it. So just because I want to see what else is going on here, my box is going to be short. It's going to be, I guess, flat and long, like this. Okay, so I'm going to just zoom in on this spot right here. Okay, so once you get that, just press enter. Okay. Based on your knowledge of visual graphing and finding the limit, what would you say the answer is? 1. Okay, and that is correct. So the limit as sine of x divided by x as x approaches 0 is 1. What it actually is here is there's a hole right here. Okay, it's a case where you do not divide and get a hole, like we said yesterday. This is a case where we get a hole. If you can tell by if you press the trace key and then you press 0, you can see there's no y value. Okay, so when x is 0 on this, the answer is nothing because we can't get an answer, but it still has a limit. The limit as x approaches 0 is 1. Okay. Now, there's some variations to this. The first variation, this is like, I'll call it 1.1 because it's really related to that one. Okay. The limit as x approaches 0 of x divided by the sine of x. It's upside down. The limit as x approaches 0 of x divided by sine of x. Any guesses of what that answer is? -1? 0? Okay. All right. You have to graph it, but you're not allowed to type it in like that. You have to think of another way to graph it. You could using the one that's there. What's another way to graph it, but you're not allowed to type it in just like that? Anybody got it? What's that? Say it again. Negative sign? Okay. You can take, so one way to do it is, if you take the vars, go to y vars, you should know how to do this now. Make sure you get the y vars and press in y1. And then you have a reciprocal key. It's x to the -1. That's the reciprocal. That's what you're saying? Something similar to that. Okay. This is the reciprocal of the first one. Okay? It's the reciprocal of it. It's below the math button. It's x to the -1. Okay. Now if you hit graph, it has the old one there, and then it draws the new one. Okay. Can you see why it goes up? It's reciprocating whatever values were here. So if you had a half here, then you have a 2 here. If you have a 1/3 here, then you have a 3 here. So on and so on and so on. Okay? All right, so what's the limit of this one? As x approaches 0, it's still the same number. It's 1. Okay? All right, 1.2. The limit as x approaches 0 of the sine of kx over kx equals. Okay, figure out the answer using your calculator. Modify the equation in some way. K is any real number. K is in the set of the real numbers. Okay, what'd you get for an answer? 0. Watch your parentheses. What'd you get for an answer? 1. It's still 1. So look carefully at this. Sine of kx divided by kx, it'd be like this. The sine of 3x divided by 3x. And you got to put the parentheses in to show that you got the numerator divided by the denominator. When you graph it, see in the picture? Okay, it's still the same hole where it was before. Okay, but look at the graph is different. Okay, it's a little bit further extreme than the last one was. It's actually condensed like this. It's pushed together. Okay. Hey, wait a second. There's a 1.3 now. I can see it on the graph. What's 1.3? The reciprocal of this one. So that one we figured out was 1, and it turns out that the limit as x approaches 0 of kx over the sine of kx is also equal to 1. This particular limit is tested on the AP exam and with some variations, which I'll show. Okay, so those 4 we got to have down, and we'll do some more practice on those tomorrow with some variations. Okay, so that was rule number 1. That's the that you got to memorize that one and its subsidiaries. 2 looks like this. The limit as x approaches 0 of 1 minus the cosine of x divided by x. This is another one it's a required limit on the exam. All right, go figure out what it is. One minus the cosine of x divided by x. Okay, did you get an answer that looks like something like this? Or you get a graph that looks something like this? Watch your parentheses. Look carefully. You got to put parentheses around the whole numerator. 1 minus the cosine of x, and then divided by x. If you don't do that, then you don't get the graph that I'm looking at here. Gosh, it looks like a sine wave. Wonder if it's a sine wave. All right, so what's the limit as x approaches 0 of 1 minus cosine of x over x? 0. Okay, that one is right here. Okay, so the answer to this one is 0. Okay. Now, this one, the wavy one here is the graph that we had. This one right here is the reciprocal. Okay, is the answer to the reciprocal also 0? No. It looks like it doesn't exist. When you graph it, it actually comes in from the left. It goes down asymptotic here. And then from the right, as you approach it, it goes up here. So from the left, it approaches negative infinity. From the right, it approaches positive infinity. And those two don't match. So the answer to the reciprocal of this one is does not exist, which is not tested on the exam. Okay. Well, if you take these and you say, wonder if this allows us to find different limits. For example, look at this. What is the limit as x approaches 0 of the tangent of x divided by x? No calculator. We'll do it analytically. The limit as x approaches 0 of the tangent of x over x. No calculator. Is there a way we can figure out how to convert this in some way so that we can get the answer? Okay, so last year you learned a lot of times take that tangent, turn it into sines and cosines, right? So let's try that and see what happens. So this would become, and notice how I'm writing this. You always write the limit again. So this becomes the limit as x approaches 0 of, okay, I got the sine of x over the cosine of x divided by x. Okay, where this sine of x over cosine of x is numerator. Okay, can we do anything with that? Algebraically, isn't this x over 1? Right? So I really have a fraction divided by a fraction. So I'm just going to rewrite it. I'm going to say this is the same as the limit as x approaches 0 of the numerator divided by the denominator. So it's the sine of x divided by the denominator. But we learned that when you divide by a fraction, you multiply by its reciprocal. So this becomes times, instead of x over 1, we're multiplying by 1 over x. So this becomes this, which becomes this. So far, so good? Okay, does that get us anywhere? Okay, I got to ask you a question. Maybe if I had the numbers 2/3 times 4/5, okay, I can get an answer to that. Is it the same as 2/5 over 4/3? Is it the same answer? Notice here, I took the 5 and I moved it here. I took the 3 and I moved it here. Both of them give you 8/15. So that's kind of a validation that, okay, it's legal to do this. So that's what I'm going to do over here. Sine of x over cosine of x times 1 over x is the same as the limit as x approaches 0 of the sine of x over x times 1 over the cosine of x. All I did was this, something you learned in 5th grade. but we're just doing it with algebra, with trig stuff. Ooh, I wish that could help us in some way. If only we knew some kind of property. Xander? Oh, okay. If only we knew some sort of property, then maybe we could do it. Yeah.
Couldn't you kind of break apart multiplication and then because the limit of Latin of x divided by x is x approaches 0 is 1.
Boom. Right there. Awesome. So, isn't this the limit of a product? This is the limit of a product. We learned in rule number 3, the limit of a product is equal to the product of the limits. So what that means is this. Now I'm going to apply that rule. This says the limit of these two things multiplied together is equal to the limit of each of them multiplied together. So I'm going to do a limit as x approaches 0 of the sine of x over x multiplied by the limit as x approaches 0 of 1 over the cosine of x. The limit of the product equals the product of the limits. Which now means we can find the answer to the first limit and multiply it by the answer to the second limit if we can find them. All right, what's the answer to this one? 1. That one you got to have memorized. Okay, so that one's good there. And can we find the limit as x approaches 0 of 1 over the cosine of x? The cosine, what's the cosine of 0? One. Okay, so it's continuous at that point, so that's no problem. So we can do a substitution. In other words, we can plug it in. So this becomes 1 times, and now I'm going to drop the limit, and I'm going to say 1 divided by the cosine of 0. I can now plug it in. We said the cosine of 0 was 1, so this becomes 1 times 1. Answer is 1. Which, by the way, on the AP test, if you can't figure something out, just guess 1. And if 1 isn't one of the choices, then guess 0. Okay? All right. This is now, what I just showed you here is we can handle more complex trigonometric limits by using some of the rules that we've established, properties and ones that we know for sure. Okay, we're going to call it a day. And homework, get as much done as you can by Thursday, because Friday might be a little bit crazy for you.